Here on page 41 of the distance learning packet, we had some slightly legible notes about the Doppler effect. And we spoke in class about the Doppler effect. I alluded to the person who made this discovery that this was mathematically related to the source of the wave and the speed of that wave in a particular medium, Christian Doppler. So there's an equation. And it turns out there's actually 4 equations. I'm looking at a college textbook here, but there is the situation where the source is moving toward an observer who's not moving toward. There's the source moving away from the stationary observer, slightly different. Actually, the equation's the same except for the plus and minus sign. But then there's a situation where the observer is the person moving, like is the case for the light we observe from. There's also this case where the observer is moving toward a stationary source and the corresponding observer moving away from a stationary source. So while saying that there's one equation is not quite true, this equation works well for the moving source, and it's approximately correct for the moving observer. So we're going to use this one equation. I have a plus or minus in the equation, and that allows me to turn 2 equations into one. We'll see exactly how we use the plus and minus in a moment. I'm just going to go over quickly the variables in the equation. F is the actual frequency, the frequency that the source is creating. F prime, F apostrophe, F prime, is the frequency perceived by the observer. So what you hear, if someone's running down the hallway screaming, what you hear is F prime, the scream is F. The one thing that confuses kids is there's a Vs divided by V. And because Doppler happens with sound a lot, people think the Vs is the speed of sound. That is the speed of the source, the thing that's making the sound. So if a car were driving down the road, honking its horn, Vs would be the speed of the car, the speed of the horn. V, the denominator, is the speed of the wave. If it's a sound wave, this is the speed of sound, little v. A quick word about the plus and minus. Clearly, if you subtract from 1 something that's small, you get an answer less than 1. If you add to 1 something small, you get a denominator a little bit greater than 1. So from a logic standpoint, you'll see why we use the plus in some situations and the minus in the other situations. But the easy way to remember it is if the sound is coming toward the observer, in this example that I found a picture on the internet, we have 2 observers. One's behind the moving car, one's in front of the moving car. But we were just talking about when to use the plus sign and when to use the minus sign. If the source is moving toward you, that means the distance between you and the source is getting smaller. In that case, you use the minus sign. And it's easy to remember because a minus is smaller and this is getting closer. The distance is getting less. If the object is moving away from you, as it is in the case of observer B, the car is moving away and the distance is growing between them, in that case you use the plus sign. So that helps you remember that if it's getting closer, we use a minus. If it's getting further, we use a plus. And that's written in here. Okay, so let's do this sample problem super quick. What I'd like you to do while we watch this video is grab your distance learning packet. This is also posted on Canvas. So just to review, F prime is the perceived frequency. F is the actual frequency. Vs is the speed of the source. The thing that's making the wave. If it's a car with a horn blaring, the speed of the car. And V is the wave speed. If we're talking about sound, we typically use a value of 340 meters per second. And of course, the plus and minus sign, if it's coming at us or approaching, we use the minus sign. And we use the plus sign when it's receding or moving away. Okay, so let's do the sample problem. The bicyclist is honking her horn, whose frequency is 215 hertz. That's our true frequency. Traveling at 37 meters per second. That's the speed of the wave source. That's the speed of the horn, the cyclist honking the horn. And if the speed of sound can be assumed to be 340 meters per second today, that is our wave speed. The first question is, what is the wavelength of the sound the horn is emitting? Well, nowhere in this Doppler equation do I see wavelength. So the only thought I have is that we're going to use the wave equation. Speed of any wave is frequency times wavelength. Solving this for lambda requires us dividing both sides by f. And when you do, you get wavelength equals v over f. Whenever you solve for either of these two things, the v always ends up on top. That might be a thing worth remembering. So let me plug in my values. And we get 1.58 meters. Now on to the Doppler shift part of the question. What is the perceived frequency heard by you as you detect that horn while it's moving away from you? Again, moving away, we're going to use plus. I didn't highlight that earlier when we were reading the problem, but let's go ahead and plug that in. So we're looking for f prime equals f over 1, in this case, plus vs over v. Let's plug in our values. The speed of the source, Vs, is the bicyclist, specifically the horn on the bike, but they're both moving at 37 meters per second, divided by 340. Notice that the meters per second on top cancels the meters per second on the bottom, and we're left with hertz. Let's do the math. Now, one thing I'd like to share with you is the use of the store and recall button. I like to do this division first, 37 divided by 340, add 1 to it, and then find out what that equals. And then I'm going to store that number so I can hit 215 divided by that number. Let me show you. 37 divided by 340 plus 1, that equals 1.1088. Now I'm actually going to hit STO1. I could have stored it in memory bank 2 or 3 as well, but I chose 1. And if I clear that and hit recall 1, it's still there. In fact, I can clear it again, and it's just still, until I store another number or a 0, that number is in my memory, 1. So let's go ahead and do the math. 215 divided by this thing I've stored, and that answer comes out 193. We already talked about how the unit's going to be hertz. It actually, to 3 sig figs, comes out 194. And there's the sample problem. Okay, and for homework, and I don't normally, tell you homework in a video, but let's cover something real quick. For homework, I'd like you to do problem 2, and then on the very next page, 4950, on the next page, there's a challenge problem. It's got 2 parts to it. You won't be able to tackle the challenge problem very well without a little background information. So let me let you know a couple things here real quick. When children are born with normal hearing, after a few months, their full hearing capability exists. And in terms of frequency, a young person whose ears are developed fully can hear sounds as low as 20 hertz and frequencies as high as 20,000 hertz. Above that, you cannot detect it. Below that, typically, a person cannot detect it. Now, as you get older, you lose the high end more so than the low, but this is the most range of hearing a healthy hearing person has. I bring this up because this problem starts out with a sound that is higher than that, and you need to know that the range of normal hearing is between 20,000 and 20 hertz, 20 and 20,000 hertz.